Okay, perfect.
Oh, yeah.
Okay, so good morning, everyone. We start now the public defense of the master thesis of Kaloy and Danowski, titled Information-theoretic Metrics for Higher Interactions on Graphs. You have around 20 minutes to present your results.
Thank you. All right. So yeah, this is my thesis defense for, well, actually not the IFISC masters, the FAMA masters, but I've done my thesis with Sandro and David from IFISC. David unfortunately can't join us, but Sandro is here. So just hello. Just a quick outline of what we're going to talk today. So of course, we'll unpack this title as we go along, which is very vague as it has to be. But first, we're going to talk about the questions that we wanted to answer as we started this research. And those questions are mostly related to higher order interactions and the distinction between higher order mechanisms and behaviors. I'm going to talk about how we answer those questions using some tools from information theory and mostly this dynamical information metric, and then discuss what we found and how we found some very interesting behaviors, even in very simple examples. And at the end, I will summarize the main product of our work, which is a set of intuitions and benchmarks that we can take for future work. So first, beginning with some context and background, it's already been shown fairly conclusively that the structure of the interaction of complex systems as modeled by complex networks affects pretty significantly the behavior of those systems and the observed dynamics. And these network effects are well documented for kind of classical, let's say, pairwise networks, but also recently increasingly for networks that have higher order interactions. So interactions between 3 or more variables at the same time. Those are usually modeled as a simplicial complex, or more generally a hypergraph. And those have been shown to affect the dynamics of the system significantly. This is an example that we also discussed in the report, is the simplicial contagion model by Jacopini, where including the higher order interactions above a certain threshold of their strength changes the transition from extinction to endemic state of the infection model to a first order phase transition. So considering the importance of these high order interactions, some researchers, in order to understand better their effect, have posed the question of distinguishing between higher order mechanisms and higher order behaviors. And in this context, mechanism refers to the dynamical rules or the mechanistic description behind the dependencies between 3 or more variables. And behaviors refers to the statistical patterns that we can observe in, let's say, in the data, and observing the system state. And this distinction is important because higher order behaviors don't necessarily lead to higher order mechanisms and vice versa. And this leads to some interesting questions, which is, when do higher order mechanisms lead to higher order behaviors? And how do higher order behaviors, how are they dependent on the strength of higher order mechanisms and on other parameters of our dynamical models? Now, as I said, it's fairly clear how to model higher order mechanisms in terms of, let's say, hypergraphs or a simplicial complex, but it's a bit less clear what exactly is a higher order behavior and how can we measure it. And if we turn to information theory, the answer that they give is that a higher order behavior is a kind of dependence within random variables that is, in a sense, irreducible to subsets of those variables. Under the partial information decomposition framework in information theory, it's been shown that the mutual information between a set of source variables and a target can be decomposed into various disjoint sets of information, of which one, called the redundancy, captures the information that you can obtain about a target from any of the source variables, whereas synergy refers to the information that you can obtain about the target only by considering the joint state of all source variables. And a few years ago, well, 5 years ago at this point, a measure called the O information was proposed to capture the balance between the synergistic and the redundant information in a system. And later, this was extended to the dynamical O information, which aims to capture the same balance within between a set of sources and a target variable that have a dependence in time. And this happens, as you can see by the definition at the bottom here, by essentially looking at the difference between the information of the whole set of sources and the target, and the information of all but one sources and the target. And of course, we condition on the history of the target so we can isolate only the temporal dependence between source and target and not any intrinsic dynamics of the target. All right, so using this dynamical information is going to be our main focus. And there's already some work that has gone in the direction of using this measure to answer specifically the question of the relationship between higher order mechanisms and higher order mechanisms and behaviors. And in particular, a study that is still in preprint by Gobiglio and colleagues showed, looked at the response of the dynamical O information to 3 clicks, so sets of 3 nodes connected only pairwise, and a 2 simplex, which is sets of 3 nodes that have a higher order mechanism between them. And they showed that the dynamical information responds responds differently to 2 simplices, and the strength of this response also depends on the strength of the higher order mechanism. So you can, if you focus here on these plots on the right, as we increase the strength of the higher order mechanism, we see that the response to the 2 simplices becomes much stronger than the response to the 3 clicks. This is kind of a promising result for applying the dynamical information, but it still leaves a lot of difficult questions because we don't really know how to interpret the magnitude of the dynamical O information. We don't know how sensitive it is to different model parameters in different dynamical systems. And also, there are some numerical challenges that we're not aware of that also the authors of this paper mention exist, but don't really look at in detail. So our ultimate motivation is to do this, is to apply the dynamical information to study higher order behaviors on large networks. And also to see if it can tell us anything about network effects in general, even without the presence of higher order mechanisms. But we believe an important first step is to gain some intuition about the dynamical information in more reduced settings. So for example, when do we see a synergistic signal? How does it depend on the strength of a higher order mechanism? And when can we use the dynamical information to reliably detect this mechanism? And the approach that we took is to characterize the behavior in very simple, reduced examples and slowly build up to more realistic dynamics and networks. And before I go into the results of that approach, this is just a kind of diagrammatic summary of the methodology that we use. So we define a dynamical system, which in general, well, all of the ones we consider will be Markovian, so only depend on the previous time step. Then we simulate it and extract a set of time series. And by varying the time index, we obtain different samples, which we use to construct a joint probability distribution between sources and target. And I remind you that the conditioning on the source time series, on the target time series, on the target history, depends on a parameter tau, which in general will take as 1, only the previous time step, but you can also extend to more time steps in the past. From this joint probability distribution, we directly calculate the mutual information and the dynamical O information. All right, so the results that I'm going to talk about will start from very, very simple examples and then build up the complexity of both the dynamics and the network structure. But since our study is very exploratory and it essentially presents a lot of simple, distinct results, we'll only focus on some key results here in this presentation. So starting off with the simplest dynamics, here is just an example of the key properties of the dynamical O information. So if you focus on panel A here, we see that for independent variables and purely pairwise interactions, the dynamical O information is 0. Then on panel B, it is negative when we have a group interaction. And panel C, it is positive whenever we have replicated information in our sources. And this is intuitively how we would expect it to work, but it already shows an interesting effect, which is that even having a higher order mechanism in our system, the synergistic response of the dynamical information can be overshadowed if there is redundant information as well, which reminds us that this measure is a balance between synergy and redundancy, not a measure of synergy per se. Another simple setup that we can look at is what happens when we increase the number of variables that we use to calculate the dynamical O information. And in this case, we'll just look at completely independent sources and targets. And we see what happens when we increase n, which is the number of source variables. As we increase n, it takes an increasingly large number of samples for us to recover the correct value, the true value of the dynamical information that we would expect. And this is an important as a kind of initial benchmark to the bias we expect with this sampling methodology that I described earlier. All right, now let's make the dynamics a bit more interesting and kind of move towards processes of spreading or contagion. We have a simple example where we have two source variables influencing a target with both pairwise, beta, and higher order, this beta triangle mechanisms. And the beta triangle is going to be a proportion, is going to be tied to the pairwise beta probability. And we see a lot of interesting behaviors actually in this simple example. One, if you focus on panel A and also on panel B, we see that we get a synergistic response even with purely pairwise interactions. Then we see cases, for example, in panel A, that the higher order behavior makes no difference or does not change the response of the O information. We see on panel C a case where the pairwise dynamics show no synergy, but the higher order dynamics, the higher order mechanism increases the synergy of the system. And also we see a case in panel B here where the higher order mechanism increases the synergy beyond that which is for the pairwise mechanism alone. And if we focus here on panel B on the point at which the increase in synergy is greatest for the higher order mechanism relative to the pairwise, we see that this happens at the point when the strength of the higher order mechanism is greatest relative to the strength of the pairwise mechanism. So this was a nice, an interesting result that we wanted to look in further. And we did that by decoupling the pairwise and higher order strengths and looking at the full dependence of this model on those parameters. And we see, as we said, that the relative strength of these mechanisms is what matters more than their absolute value. So if you focus here on the right, the blue line shows us what happens when we have no pairwise mechanism and only a higher order one. We see that the dynamical O information is heavily affected by the value of the higher order mechanism on this x-axis here. But as we increase beta, we see that the effect becomes smaller and smaller until at the beta equals 1 extreme, where that pairwise interaction is strongest, the higher order mechanism makes absolutely no difference to the dynamical O information. So this is a very interesting interplay between these parameters. And then complicating even slightly further the dynamics by adding infection and recovery to the source variables, we see we obtain results that, among other things, most importantly, tell us about the importance of the conditioning on the target history. So far, conditioning on more than one time step in the history of the target made no difference. But now, if you focus on the difference between panels A and D here, we see that conditioning on 2 time steps, panel D, is necessary to reconstruct faithfully or to isolate correctly the effects of the sources on the target. All right. And for the last set of results, we focus on more interesting network effects. So here we see a situation in which we have one source variable broadcasting its information to a set of intermediate nodes and a target which undergo these both pairwise and higher order infection. And we see that in this case, compared to the more basic case we showed at the start, over here, we see that the region of maximum synergy, the maximum synergistic response of the dynamical information, is actually shifted. It appears for intermediate values of beta and mu, and for large values of these parameters, we actually see redundancy. And what's more interesting is that if we activate the higher order mechanism, this region of synergy actually shrinks and the region of redundancy arguably expands. This is a very interesting counterintuitive result, and it might show us that the structure of the network and how information is propagated through it also affects heavily our ability to detect higher order mechanisms, not just the parameters of our model. And the last example, the last result we show here is actually taking a network, a small network of 20 nodes that undergoes SAS, purely pairwise SAS dynamics, and taking a single target node and looking at its dynamical O information between that node and its first, second, third nearest neighbors. And we don't necessarily study why the value of the dynamical information approach is 0. We've seen that that can be affected by many things. What I want to show here again is that we expect some numerical challenges for applying this kind of methodology to even moderately sized communities. As you can see, it takes a lot of samples and a lot of computation time to approximate this correctly. All right, so that's it for our results. And very quickly, let's just bring it back and say that the most general observation we can make is that this dynamical information is useful as a measure of higher order behaviors, but it's kind of tricky to use because its magnitude and the effect of adding a higher order behavior really is very sensitive to the specific dynamics and model parameters. And also, we've seen quite a few concerns regarding the feasibility of this approach for studying larger communities and networks. And in terms of the interesting questions that we posed at the beginning, we see a pretty large array of different behaviors, different dependencies between higher order mechanisms and behaviors that are not necessarily trivial, that we didn't expect, and are not always even very intuitive, which is interesting and kind of encouraging in the sense that it tells us that dynamical information could be used to explore this intricate relationship. But we have to be realistic and say that the results we show are not very conclusive and are still a little bit far from the ultimate goal that we have of applying this to bigger networks. And that's largely because our study was very exploratory. And we think as such, it provides very good intuitions and initial benchmarks that we can use for future work and for applying the dynamical information in the future. But really, our main motivation after these kind of reduced models is to see what changes when we add the rest of the network. And we think this can be done feasibly, despite the concerns we had before, by having kind of smarter implementation and using some computational tricks. We have an idea of how to do that. And what exactly do we want to do? Well, the benefit of having a very exploratory work is that it opens up a lot of avenues for further research, right? So one is that we can keep studying kind of reduced examples and characterize better the dependence in those cases. But perhaps more interestingly, we can study different dynamical processes, contagion processes, opinion dynamics, and even continuous dynamics like synchronization in the Kuramoto model. And perhaps most importantly, study larger network scenarios in larger networks and see what is the effect of having different heterogeneous network structure on the response of the dynamical information. What are the network effects coming from the local neighborhood of nodes? For example, how does the dynamical information depend on the neighbors of the node and how many neighbors it has? How does it change within communities or within different particular network motifs are all interesting questions for us. And lastly, going more into depth into understanding the relationship between mechanisms and behaviors in the higher order setting, I can have some very interesting applications to network inference or the problem of reconstructing networks with higher order interactions from data. That's all I had. Thank you for your attention. And thank you to Sandro and David, my supervisors, for, of course, all of their help with this and everything they taught me during this work.
Thank you for your presentation and keeping that in time. Now is the question time. Before we start.